In the last chapter, we looked at a rock falling. We looked at the average rate of change. We looked at the instantaneous rate of change using all sorts of algebra stuff. Now we're going to start using calculus. The definition: instantaneous rate of change. The instantaneous rate of change of some function f of x with respect to x at some value xo is the derivative at that value x sub 0. It's the limit as h goes to 0, x plus h, f of x over h, if it exists. So basically, what are we looking at here? Remember, how did we find the instantaneous rate of change in the last chapter? Remember, I gave you that graph and you had to find how it got closer and closer and closer. You have to estimate what it was. Now we can find the rate of change, the slope of the line tangent to the curve at any given point by finding the derivative. Does this look familiar? Yeah, it's a difference quotient. As h goes to 0, it becomes a single point. It tells us the slope of this tells us the slope of the line tangent to f of x at x sub 0. So that's what the first derivative is all about. Example 1. What does this formula represent? D stands for diameter. What is a diameter? How do you define a diameter of a circle? If we had a circle, what is the diameter? Well, from the center to the circle is called a what? So all the way across through the center, that's the diameter. So the diameter is twice the radius. So we know we have the formula of the area of a circle at any diameter. The question is asking here is how fast does the area change with respect to the diameter when the diameter is 10 meters? How fast does the area change with respect to the diameter when the diameter is 10 meters? What am I trying to find here? Yeah, a rate of change. So the rate of change we defined as being what? The derivative. So we have to find the derivative of our area. We're looking for the derivative of the area with respect to the diameter. That's important because originally we would look for x. We don't have an x in there. So what are we changing in this function? The diameter. Because think about of a pond. If you throw a rock in a very calm piece of water and you throw a little rock in the middle, what do you see happen? You get these circles that keep on growing. So at any moment, you can see what the rate of change is and how big that diameter of that circle is going to be just by looking at a couple of time intervals. So the pi over 4 is a constant. We just leave that alone. So what's the derivative of d squared? 2d, which the 2 and the 4 cancel. So we get pi over 2d. That's our area that's our rate of change. So when it's 10 meters, how much does it change? So we have the area is pi over 2 times 10. Yeah, it becomes 5. So it changes at a 5 pi radius per unit interval. So that's what we're looking at. That's the instantaneous. At any moment, we want to see the diameter of the circle. How fast is it changing? It's changing at 5 pi units of time. Now let's look at motion problems. In motion problems, what do we call, how do we derive, how do we change in motion problems? We begin with what? So if you're looking at a motion problem, you have to begin with some object someplace. It's going to change with time. So we just call it S of t. Now, as that spot moves, so this goes from T1 to T2, it's just moved some far. What do we call that movement over the period of time? That's the change of S. So the S function is what we begin with. That's a position where we are. When we start changing it, we call it the velocity. The velocity is the change of S over the change of T. What this means, it's the first derivative of our function. That's what velocity is. It's the change of position of our object over time. So the velocity is the first derivative of our position function. This is our position. So the velocity is the first derivative of position. Now, what happens as your velocity changes? So as your velocity changes, we get something called acceleration. What the acceleration is the change of velocity over the change of time, which is the first derivative of velocity. So since acceleration is the first derivative of velocity, that means it's the second derivative of our position function. It's the change of change of position of our function. There's one more. Whenever you have change of acceleration, a lot of people never heard of this. They call that a jerk. A jerk. So it's a J of t. The J of t is the change of acceleration over the change of time, which is the first derivative of acceleration, which means that's the second derivative of velocity, which means it's the third derivative of your position function. You see how all these are connected. So what does let's look at velocity. So the function for velocity, remember, it's the first derivative of the position function, which means it's the limit as our delta time goes to 0 of our function f of t plus delta t minus f of t all over delta t. Because our h is now our t. This is t1, this is t2. This area inside, this distance here is delta t. So from t1, we add delta t, we get t2. So that's the same way we derived our distance function. One last thing. So that's velocity. What is speed? What is speed? We use the term all the time. What does it mean? How fast it's going. In other words, how you determine how fast something's going is how far you've traveled over the period of time. So it's the velocity. If you're going from here to Fort Worth, and then from Fort Worth to here, does your speed change? In other words, if you're going 50 miles an hour going that way, is it negative 50 going this way? No. So it's absolute value. So speed is the derivative of your position, is the absolute value. And we'll pick up from here next time on Thursday. Yeah, so we should be able to finish chapter 3 by the end of next week because it's got 9 sections in it.